So when we talk about the kinds of effects that drugs have on the body, they're going to fit into two different categories. We've got specific effects and non-specific effects. So specific effects, these depend on having a particular amount of the chemical in the body at a certain time at a certain concentration. So these are what we call specific effects. If you drink an 8-ounce beer in 15 minutes, or if you drink an 8-ounce beer over the course of 4 hours, the effects that it has will be very different. And then if you take that 8-ounce beer that you drank in 15 minutes and then you drink 3 more at 15-minute intervals, those are going to have very different effects than, again, that 4 hours that it would take to consume one. So depending on how much of the drug is consumed over what period of time, we can see different kinds of effects. And then we have this other category called non-specific effects. And the major effect that we'll be talking about here is the placebo effect. And these are the effects that the drug has, which are moderated by the user's background, their expectations, their perceptions, and the environment. So we're going to talk a little bit about the placebo effect because people tend to find it very interesting. Where that name comes from is through an experimental process called a double-blind procedure. So in a double-blind procedure, neither the people who are participating in the experiment nor the researchers know whether the participant is receiving an active drug or a placebo. Think about a clinical trial for a new drug. If a manufacturer wants to market a new drug for a condition, they need to prove that it's more effective than the drug that's currently being used in for that condition that's currently being marketed. So they're going to take a group of people, they're going to divide them in half, and they're going to give one group of people the new blood pressure pill, and then the other group of people will not be getting anything. Well, there's a couple problems with that. First one is that if people have high blood pressure, they need to be under treatment. And then the second thing is that when people who participate in the experiment know what's going on, their reactions and their expectations tend to be different. So it is a scientific standard that if we're doing this kind of experiment, then the people who are in the control group, the people who are not getting the new medication, they will get some kind of sugar pill, some kind of pill that's not chemically active, or some kind of treatment that seems like a treatment but doesn't actually have any physical effects. So this helps us to control for those non-specific effects, people's expectations about what's going to happen when they take the drug, and allows us to truly evaluate the effectiveness. Now, once the trial is over, then the participants and the subjects do find out whether the person was receiving the active medication or the inactive or inert placebo. So placebo effects, again, these are non-specific effects, and they're caused by the person's beliefs about what the drug should do. This really speaks to the incredibly powerful connection between the brain and the body. And I've got a quick video I want to show you about that placebo effect.
Now, you've all heard of the placebo effect before, when something with no known therapeutic value can actually make people feel better. It's a great trick our minds play on us, that by believing and expecting something to work, it actually does. But what's weird is that the strength of the effect can differ for some really strange reasons. For example, the same placebo can treat pain half as well as aspirin, while at the same time treating pain half as well as morphine. Morphine's a much more powerful painkiller, but a placebo is half as effective as both. Saying a placebo will reduce pain reduces pain, but saying that the same placebo will increase pain increases pain. Believing that a placebo will make you feel better will make you feel better. Believing that it won't has the opposite effect. Now, placebos aren't just pills. They can be creams, injections, surgeries, or drinks. You can even get placebo buttons. They don't actually do anything, but they sure as hell make you feel like you're in control. But not all placebos are equal. The effect of the placebo is bigger when the pill itself is bigger, or if you have 2 instead of 1, or 2 once a day instead of 1 twice a day. And a capsule will usually beat a pill, and a syringe will usually beat a capsule, and anything with a big ass science machine can outperform any of them. A plain pill works worse than a branded one. A discounted pill works worse than a pricey one, and even a pill in a plain box does worse than one that's all shiny and shit. Placebos that are blue work best as downers, and placebos that are red are better as uppers. Studies have shown that people who take their meds on a regular basis are less likely to die than those that don't, even if those meds are all placebos. You can even get addicted to placebos. In one study, a group of women took placebos for more than 5 years. 40% of them suffered withdrawals afterwards. In fact, the effect of placebos can be so strong that some people want them banned from sports. But I mean, how would you even test for that? Placebos don't even seem to work from place to place. For example, in Germany, using a placebo to treat ulcers works better than anywhere else in Europe. But using a placebo that treats hypertension doesn't work nearly as well as it does for its neighbours. Now, remember that all of this is about comparing things that both have nothing medically effective in them, which goes to show that a placebo isn't about what's in it, but about the beliefs that we load onto it. Our minds create the medicine, and that is pretty freaking weird.
Okay, so there's a little bit of language in the video, but it does do a great job of explaining this really complex idea called the placebo effect. So the most important thing to remember about a placebo is that it has no medicinal content. It is inactive. And based on all we know about drugs and drug actions, it should have physically no effect on the body. But because of that really powerful connection between our brain and our brain is able to create an effect for the drug that isn't there chemically in the substance or the treatment that we're taking. We do find that placebo effects tend to be most powerful for the symptoms of pain and depression, and there are some studies that suggest that they're responsible for up to 80% of the effect of antidepressants. But before you write that off, before you say that there's nothing to antidepressants because 80% of it is the placebo effect, keep in mind that those substances are dramatically improving quality of life for folks who are taking antidepressants, that it is a clinical condition and an effective treatment for it. So a really complex subject and one that we can have some pretty interesting conversations about. Do let me know if you have any questions about that. So specific and non-specific effects. When we talk about non-specific effects, we're really talking about the placebo effect. When we start talking about specific effects, we're going to start talking about the dose of the drug. So we're going to talk about this thing called the dose-response curve. And basically, this is a graph that's going to represent the relationship between a drug dose and the effects that it has. We're going to define some vocabulary words as we go through this, and we'll start with threshold. So the threshold is going to be the lowest dose at which we can see some effects from the drug. And just keep in mind that since drugs have multiple effects, single drugs have effects on multiple body systems, a single dose response curve won't really represent all the effects of the drug. So we'll be creating multiple drug dose response curves for the different effects the drugs have. Multiple dose response curves for the different effects the drug has on the body. Okay, so here's what one of those dose response curves would look like. Down here, where we first start seeing recognizable effects, this would be the threshold. In this particular case, we've got 3 different dose response curves, and these are for, the different effects that alcohol has on the body. So across the bottom, we have varying doses of alcohol, low to high. And then up on the left side, we've got the percentage of individuals who show the effect. So at low doses of alcohol, we see a small percentage of individuals showing a slowed reaction time. As the dose of alcohol increases, then we see the percentage of individuals who show that slowed reaction time increasing as well. And then at the far end, we've got coma. So we see having to start with a higher dose before we see any threshold of that, before the threshold of that appears. And then that increases at the same rate as the symptom of slowed reaction time. So that's what a dose response curves look like. And this is one that has multiple curves for multiple effects of the drug. So if we look at that again for alcohol, we've got increasing dose going across on the bottom, and then increasing response going up on the left side. So this would be for an individual person as we increase the dose of alcohol. So we start with no effect at the lowest dose as we begin to consume the alcohol. And then we move into that kind of giddy or euphoric phase, maybe that buzzed feeling. And then as the dose increases, we may get sleepy. It may become a deep sleep, perhaps loss of consciousness, and then possibly difficulty breathing. And then if the dose were high enough, we could actually see death as a response to that extremely high dose of alcohol. So these are different ways that dose-response curves can work. Another thing that we're going to be looking for as we look at the effects of drugs is something that we call the safety margin. As a drug gets developed and released into society, we want to make sure that people are taking a safe dose. So the safety margin is going to be the dose that produces the desired effect in the most patients, and then the lowest dose that produces an unacceptable reaction. Okay, so we're looking for the dose that is the safest. And one thing that this will depend on is the potency, or the amount of drug that's required to produce the effect that we're looking for. And then, of course, almost all drugs have some kind of side effect or an unintended effect that comes along with the effects that we're looking for. And again, this is because most drugs do affect multiple body systems. When we're estimating the safety margin, we're also going to be looking for the effective dose. So the effective dose, this is the dose that produces the meaningful effect in a percentage of test subjects. It can be for any percentage, but the percentage that we deal with most often is the ED50. So this is the effective dose for half the animals in a drug test. And many of these statistics are based on animal testing. So the ED50 is what represents an effective dose for half of the animals that participated in the trial. And then a little further down the line, we've got the lethal dose. So this is the dose of the drug that has the lethal effect in some percentage of test animals. Again, it could be any percentage. The convention is to use 50%, so we've got the LD50, or the lethal dose for half the animals in a drug test. And as if I'm discussing this, you're having some ethical concerns about use of animals for this type of testing. This is definitely an emerging concern about this type of testing and developing these statistics as well. It's not something that we've reached a new norm for, but it's definitely something that's become an increasing concern over the past several decades. So then we're going to talk last about something called the therapeutic index. So the therapeutic index is the LD50 divided by the ED50. So we're going to take that dose that kills half the animals in the test, and then we're going to divide it by the dose that is effective for half of animals in the drug test. And we end up with this statistic called the therapeutic index. And then based on the math involved, this statistic is always going to be greater than 1. So these are the numbers that we use to calculate what we call the safety margin for a drug, a new drug that is being released to the market.